Hello and welcome back to the May 2025 TZ2 IB Chemistry Exam walkthrough. We're so close to the end. I think maybe 2 videos left for the HL portion of paper 2. If you want to see the marks that are in common with SL, look at the playlist here. It's a million years long. Okay, let's get going. So this is question 3, the question 3b. And so starting off with this 3b part 5 of the question, it is just a standard entropy question. And so it gives us it's asking us to calculate it for the reaction between carbon monoxide and chlorine to form phosgene and to use section 13 of the data booklet. And so we had already stated previously that we had this kind of equation going on of our carbon monoxide chlorine to form phosgene. Everything's in a 1-to-1 ratio because it's all balanced. And so this does require us to look at the data booklet to find the standard entropy of because it gives us the chlorine and phosgene, so we just need to find carbon monoxide. So we're going to go over to the data booklet, and we're going to find da-dee-da-dee-da-dee-da-dee-da. Oh, I think I passed it. There we go. We're going to look for carbon monoxide, which is right there. And so we're going to go over to this last column, and I already lost it. There we go, carbon monoxide. So it is here. So it is 198 for our entropy. So we're going to use that. And so for our entropy, it's just going to be products minus reactants. And so our products are going to be the 284. Meanwhile, our reactants is going to be 223 plus, I already lost it, 198. Okay. And so we're going to just write that down, 198. Okay. And so that is going to end up giving us, if we just put it into our calculator, negative 137 joules, moles, Kelvin, negative first. Okay. So that is that part 5. For this part 6, it says to deduce whether the reaction would go to completion or reach equilibrium at 298K. And it says to use our answers from A3, so that was our enthalpy, and AV. Oh, this was A. Sorry, my bad. Anyways, part A. And so both our enthalpy and our entropy. And so that is already immediately enthalpy entropy. We need to solve for Gibbs free energy. Okay. And so we're going to immediately do that. And then since it asks us to figure out about equilibrium, we can use that to then solve for the equilibrium constant. Okay. And so we're going to solve for our Gibbs free energy, which is going to be equal to, this equation is in the data booklet, but you should honestly just remember it at this point because it's so common. The change in enthalpy minus T change in S. And so whenever you're doing this equation, you always need to remember your units or else they will get mixed up because enthalpy and entropy have different units. You need to make sure they match. Okay. I usually just tend to make my enthalpy match the entropy. So it's in joules. So we have from part 3, we had that our enthalpy was negative 133 kilojoules. We're just going to go ahead and convert it to joules in this calculation. So negative 133 times 10 to the third joules per mole. And then minus our temperature it says at 298K. 298K. So we're going to put 298. Okay, and then we had our entropy from the other page as being negative 137 joules, moles, Kelvin. Okay, so if you put that in your calculator, you end up getting negative 92,174 joules per mole. And so then we can go over to our data booklet where I actually don't have this equation memorized very well, is the Gibbs free energy and equilibrium constant equation. So that one is right here. So the Gibbs free energy is equal to negative RT ln K. And we're going to solve for K. Okay. So we're going to go over here, back to our guy. So we have that the Gibbs free energy going to be equal to negative RT ln K. We're going to solve for K. Before even putting in any numbers, we need to just rearrange the variables in the equation. And so we have that ln K is going to be equal to the Gibbs free energy divided by negative RT. And so just like the logarithms is if you have that log xy is equal to something, you can do the exponent. It's similar with ln. So if you have like ln y is equal to x, that is the exact same thing as e to the x is equal to y. So we can use that for this equation. So we know that k is going to be equal to e to the Gibbs free energy divided by negative RT. So we're going to go ahead and put that in there. So we have E. Gibbs free energy is we have it already in joules per mole, which is good because our R, let me find it, R is also in joules, Kelvin, negative first, mole, and negative first. We need our joules to cancel out. If you didn't already have it in joules, you would need to convert it to joules at this point. Okay, so E to the 92174 joules per mole divided by negative 8.31 joules, Kelvin, negative first, mole, negative first, and then just times our 298. K. And so if you put this all in your calculator, you end up getting that K is equal to this 1.46 times 10 to the 16th. And so you may want to stop here, but you need to remember to read the question and also remember there's 3 marks. So this makes sense with the 3 marks that you're going to be calculating Gibbs, calculating K, and then finally answering the question, which is whether this reaction would go to completion or reach equilibrium. And so we're going to say K is giga large. And remember, K is just the concentration of products over reactants, right? Sorry for that random lag. Sorry, we were over at this question where we were saying that K is giga large, which is greater than 1, and so obviously not equal to 1. Therefore, the reaction is not at equilibrium and would go to completion in the forward direction. Complete. Forward. Okay, so you would essentially, so that matches with the 3 marks in that question. Moving on to B3 is this is continuing on with this reaction of phosgene decomposing in the environment. So with some steam into carbon dioxide and hydrochloric acid. And so it says to write the rate equation if the reaction is first order with respect to each reactant. So rate equations are always rate is equal to K, and it's just the concentration of each reactant with the order. Since it's first order, it's just going to be the concentration of each reactant. If it was second order, it would be raised to the second, but since it's first order, it would just be that. So it'll be CO2, CO, so our phosgene, as well as our water. Okay, and so since they're both first order, is you can imagine that they're both raised to the first, but since they're both just to the first, you also don't have to write it because that's just kind of redundant. Okay, so that would be that rate equation. For this part 4, it says that if the reaction occurs in dilute aqueous solution of phosgene, it appears to be first order overall. This is contrasting to the rate equation that we just wrote, because the overall order, even though it's first order with each reactant, would be second order. 1 plus 1 equals 2, right? And so this one is saying that if you dilute aqueous solution, then it appears to be first order overall. And to kind of explain why this is, okay? And so in order to kind of determine the, what's it called? Like order of reaction, you have to change the concentration of each reactant, right? And so if you're changing the concentration of phosgene and it is just if it was, and it's just mostly water and it's not barely any phosgene at all. Okay. And that would essentially mean that the amount of water in the reaction is staying constant the whole time. Okay. And so whenever you have that, like, because in our rate equation is K is a constant. Okay. The only reason why these two are here is because they're constantly changing, right? They're not constant. Okay. And so K is constant. So whenever you have almost completely water, water then becomes constant. And so that means the rate equation ends up just kind of being K, just depends on the concentration of phosgene. Okay? Because then just concentration of water is now constant. So it's kind of just absorbed into the rate constant because it's staying the same the whole time, no matter what. It's just very large number. Okay. And so I ended up just saying that because actually, let me find exactly what I put whenever I took this myself. Is I put exactly, how did I word it? Is I said that because a dilute, we're not gonna write the wordiness. Is I essentially said because a dilute aqueous solution of phosgene would have almost entirely water and barely any phosgene. Entirely water, barely phosgene. And this was accepted. So there were two options in the mark scheme, where the mark scheme either accepted if you said something along the lines of that the concentration of water is greater than COCl2, the concentration of phosgene. So I felt like my answer aligned with that, but they also accepted it if you just said that water is constant, the concentration. Okay. Weirdly enough, though, the way they wrote this in the mark scheme is they have these two side by side, but rather than putting a comma like I did here, is they put like a slash. And so I actually initially read this as the concentration of water is greater than phosgene divided by water. And I was like, why would that matter? I was really confused. And then I was like, wait, no, that's just saying an alternative answer. Okay, that's weird. Anyways, so yeah, that is that one. And then this 5 says the activation of this reaction was found by measuring the reaction rate over a range of absolute temperatures. The following graph was plotted. Okay, you should immediately start thinking Arrhenius equation. Crazy. And so if you go look at your data booklet, we have the Arrhenius equation, which is we have both the kind of exponential form, but this is not an exponential graph. We need it to be a linear form. And so we actually are also given the linear form right here. Okay. And so we need to see, okay, what is the x and what is the y? Y is equal to mx plus p. So our y would be ln k. So we'll put that over here, ln k. Meanwhile, our x would be, we know it has temperature in it. Temperature is in the denominator, so it would be 1 over T. Boom. 1 over T. And then for part 6, it says to calculate the gradient of the line on the graph if the activation energy is 12 kilojoules per mole. And so we already said that looking at this equation, that 1 over T is our x. So that means that our slope, our m, would be negative EA over R. Okay, so our slope is going to be equal to negative EA over R. Gradient, slope, same thing. I just use them interchangeably, sorry. And so it says to calculate the gradients. That's just what we're calculating, and it gives us our activation energy. So our activation energy would be negative, and it tells us it is 12. Except our R always is in joules, not kilojoules. So we need to go 12 times 10 to the third joules per mole divided by our 8.31 joules, Kelvin negative first, moles negative first. Okay, and then that would end up getting us this negative 1,444 Kelvin. Okay, and that would be the gradient of the slope. And I think that's the end of, that is the end of B. So that's the end of this video.